All right, our DAG example application is coming along quite nicely. At this point in time, we are able to make new transform nodes. Of course, these new transform nodes are at the root of the scene. We also have the set parent functionality working nicely so that we can take transform nodes and parent them to one another so that we can create hierarchies. The one thing we are missing, though, is the ability to display what the hierarchy looks like. And this is about to become very important. Why? Well, as we continue working with the transform node class by adding more and more functionality, it would be nice to be able to verify the results of this functionality that we add. Things such as remove nodes or even group nodes, it would be nice to turn around and display the hierarchy to make sure that the functionality that we called upon worked properly and that the render of the hierarchy is reflected properly. So what we're going to do in this video is focus on getting the ShowTree method up and running so that we can render out a very basic representation of the hierarchy. Now, what we have to do is use a technique called recursion to do this. What I'd like to do is jump over to Photoshop and do a bunch of drawing. So let's start out by adding a new whiteboard in, and we'll drag this whiteboard up to the top. We'll hide this other one. And let this whole thing begin with us drawing a very simple hierarchy that we would like to be able to represent on the console with a simple render. So let's see, what is the hierarchy going to look like? Let's start out with node A. I'm going to make these transform nodes a bit bigger than normal. So node A, and inside each of these transform nodes, they contain a list of children. All right, so node A is going to have, let's say, 2 children. So we'll have a node B. And node B, of course, is going to have a list of its children. Now let's go ahead and add node B up here into the children list for transform node A. Let's create another transform node that's parented to A. And let's call this one C. And of course, C is going to have a list of children as well. Now let's add C up here. Very nice. Now let's say B has 1 child. So let's go ahead and create one transform node. And it is a child of B, and let's call it D. Gotta love my creative naming here. Of course, he has his own list of children. And now let's add D to transform node B's list. There we go. Now let's say C, to make things a little bit more interesting, let's give C 2 children. Let's start out with transform node E. We will, of course, give him his list. And transform node F. And we'll give him his list. Now let's make sure to add both E and F to the children's list of transform node C. Okay, so this should be a fairly accurate representation of what the nodes are going to look like inside the heap in regards to each of the transform nodes' children list. Agreed, Logan?
Agreed. Obviously, it's not going to be arranged in memory in a tree.
No, not in a tree fashion. No, it's all through linkage, if you will.
The linkage will be, yes, the linkage will be accomplished in the list as drawn. So A will have B and C, B will have D, C will have E and F.
That's right.
That will perform the actual linkage.
But what we want to do is we want to get a representation of this on the console in such a way that we are able to quickly distinguish which transform node has children. Okay? So what do we want the actual console to look like? How about a child is simply represented as 2 dashes in from the parent?
So a 2-dash indentation.
So a 2-dash indentation. So we'd start out with A. A is at the root of the whole scene. So he would have no dashes at all because he's at the root. Now B is a child of A. So he would have 2 dashes in from its parent, A. So this would be B. Now, B has, before we move on to C, B has a child, and that child is D. And that needs to be 2 dashes in from B itself. That means 1 dash, 2 dash, that just gets us over to the level, if you will, of B, or you could say the depth of B. Now we need 2 dashes. 1, 2. And now we can go ahead and put D. So D is a child of B, which is a child of A. All right, now let's go ahead and do C. C is a child of A. So 2 dashes. 1, 2, and then we write C. Now we need to write E and F. E and F are both children of C. So we need 1, 2, now 2 more to represent that it is a child of C, and we can now draw E, and 1, 2, 3, 4, and we can draw F. That is the result that I would like to see our ShowTree method generate. This is a good representation of the hierarchy that we have. Now let's take a look at depth. If we were to come in here and divide this thing up, so I'll just put a whole bunch of dashed lines right about here, and a whole bunch of dashed lines down here. Couldn't we say that this would start out at depth 0? Hang on, that was horrible looking. This starts out at depth 0. Then we could say that this would be at depth 1. And then down here we are at depth 2. Now in determining how many dashes that we draw, how about we use the depth of where we're at times 2 dashes. So if we were at the root level, so to draw out A, the depth would be set at 0. 0 times dash dash would be equal to what?
Nothing.
Nothing.
String.
So it'd be empty. Nothing at all. So now if we step down into the level of B and C, so you could say depth 1, we would have 1, and 1 times 2 dashes would be equal to what? 2 dashes. And let's just go ahead and start putting these. We'll put them in double quotes. So up here would just be a set of nothing. And then if we step down into the level of D, E, and F, they're all at depth 2. So 2 times dash dash would be equal to what? 1, 2, 3, 4. Okay? So 2 sets of them, if you will. So looking at this very simple scenario that we're setting up with the depth times a set of these dashes, you can see how that quickly will indeed generate the number of dashes that we are using over there in the rendered output on the console, right?
Right.
Okay, so now what do we need to do to make all this work? Well, we know that ShowTree is an instance method. Okay, that means that ShowTree belongs to all of these nodes. So he has his own ShowTree. In fact, let me just say it's called ST. So ShowTree, he's got a ShowTree, he's got a ShowTree. They all have a ShowTree that's their own instance method. This is very important to understand in regards to what's about to happen. What I would like to do is basically take advantage of that private void ShowTree that we created a skeleton for a little bit earlier. And if you recall, it takes in an int depth. Now inside here, what I would like to basically do is figure out my padding. What is padding? Padding is just going to be a very simple string variable. By the way, this is pseudocode, okay, so don't look at anything here being hardcore code. We'll do that in just a minute. So padding is going to be equal to my dashes times whatever my depth currently is. So then I could just turn around and say, write out what my current padding is plus the current node. Okay? Now, let's think about this. If I start out by calling transform nodes A show this method. So who is this? This is transform node A because that's who we're looking at, node A. I would send in a depth of 0. Starting out with 0, the first thing that's happening right here is I'm calculating what's my padding going to hold. Dash dash times depth of 0 is nothing, so padding is just emptiness. So then I would turn around on the next line and I would print out nothing plus this, which would just result in A being printed out. Okay? So now, let's go ahead and remove those two to keep things kind of clean. If we were to turn around and do a for each, this is where the power comes in. So for each transform node, again, I'm just going to abbreviate TXFRM. So for each transform node, and we'll say it's going to be called child, in children. So what we're going to do is we're going to walk through this node. So in the case of us calling upon transform node A's ShowTree method, this is A. So we're going to take a look at all of the transform node children being stored in node A's children list. Okay? Now what are we going to do with them? We're going to call on each of those transform nodes. So child dot, we're going to call on their show tree. And we're going to send in the current depth that we have here plus 1 because we just stepped one further down. And that is, of course, it's 70% pseudocode, but that is all we're going to be creating right there. But what we need to do is we need to trace this out so that it makes complete sense. So to trace this out, let's do some pseudo stack tracing. Okay, a lot of pseudo stuff going on here to keep the drawing simple. So let's start out somewhere, let's see, right about here. Bear with me. Trying to put some relatively neat lines in. Okay, so starting out, when we call, let's say we start out at A. So we're going to call upon A's show tree. And what are we going to send in as a depth? 0. So what I would like to do is represent A down here. So here is the object A. The object A contains some data storage devices. It contains a list. Inside that list of children is B and C. It also contains a local variable. It contains that parameter depth. So here's depth. And what's stored in depth? Well, when we called upon A's show tree, we kicked the whole thing off by storing a 0 in there. Okay? So we're storing a 0 in there. Now let me go ahead and start about right here. And we can say that this is a stack frame. So all of our visibility is stuck right in here at the moment. Now let me go ahead and create another console that we can write out to. So this is the console that's going to be resulting, or it's going to provide the result of the code that we just put in place there. Okay, so what happens? We called upon A's show tree. We sent in 0. We start out by first calculating our padding. Well, we know that padding is going to be 0 of those dashes because our depth is currently at 0. So 0 times the dash dash is going to give us none of them. So we're going to print out padding, which is nothing, plus this. This is A, thanks to the overload that we put in, or the override, excuse me. So let's go ahead and come in here and print out A. Very simple. Now we're going to come down here and we're going to do this for each. Ooh, this is where stuff gets fun. So for each child in children. So our attention just shifted to over here, and we're looking, that's an arrow, we're looking at B, okay? Now, what I'd like to do is go ahead and call B's show tree. So now we're in a new stack frame. Object B. Object B has his own list of children, and he has his own local depth parameter. So the children that are in B is simple. It's just transform node D. And what is our depth? Well, For each child that we call upon, so we're starting out at the first child, we're calling that child ShowTree, and we're sending our current depth plus 1. Our current depth, this was the calling location, is 0. So 0 plus 1 means down here in the stack frame for object B, in his ShowTree, depth is 1. Okay, very nice. So what I need to do is let's go ahead and, oh, we managed to lose our eraser. Very nice. So here we are at this point again. So padding is going to be equal to dash dash times depth. So we could say that here we've got padding, I'll just say pad, equals dash dash. Okay, because our depth is 1, so 1 set of the dash dash. All right, so now we come down here to the write it out. So we're going to write out the padding plus this. So we're going to get dash, dash, and this is B. So we get B. Very good. So far it's looking just like the result that we were hoping to get over in the left-hand console representation. This guy right here. All right, very good. So now we come down to the next line, which is, and again, we're inside B's ShowTree method. So now again, we're going to do a for each. So for each transform node in child. Or in children, excuse me. So B does have a child that's in that children list, and it's D. So we're going to start out by pointing right here at D. So let's go ahead and we're about to start a new stack frame because we call upon the child's ShowTree. So here comes D's ShowTree. So there's D. D has his own children list, which fortunately is empty, so we don't have to trace forever. He contains his own depth. What's depth going to be? Well, the caller was B, and B's depth was what? It was 1. So 1 plus 1 gives us 2. Wow, look at the logic. It's lining up because D is indeed at level 2. So now what's pad going to be equal to? Pad is equal to 2 times those double dashes. Okay, so that means we're going to get 4. 1, 2, so that's one set. 1, 2, that's the second set. All right, so next line, what are we going to do? So we just did this line. Now let's do the next line. Print out the padding plus this. So the padding is 4 dashes. So 1, 2, 3, 4, and a D. Taking a look over there at this guy, we're looking pretty good. Excuse me. Okay, so now, again, we fall down here to the for each for transform node D. And once again, it's going to be for each child and children, we're going to call the child's ShowTree. Does D have any children? The answer is no. Okay, so that means we are done with D. So with us being done with D, this whole line, this whole stack frame is removed. And we return back up here to the caller. All right, so now that we're back in the caller, where does that mean we're at? That means we just finished calling the first child's ShowTree. Now we wrap back around to grab out the second child and children. Well, are there any more children inside of B's children list? Answer, no. So what's going to happen? We are going to remove this stack frame and return back to its caller. So that brings us back up here. Same exact thing happened. So now we're back at A. We're inside the for each loop. We just finished this line right here. So what do? We grab the next child in children. Look at this. The next child in children is C. So what are we going to do? We're going to call on C's. We're going to call on C's ShowTree. Okay? So let's go ahead and do that. So let's come down here and create a brand new stack frame. So here we are with object C. And of course, C has a list of children. It has E and F. and it also has depth. What is its depth? Well, that depends. The parent's depth, who was the parent? The caller of this? The caller was A, right? Remember, it was right here where we called upon it. So what was his depth? His depth was 0. 0 plus 1 is 1. So C's depth should be 1. Let's take a look at our little representation with the hierarchy over here. Look at this 1. C is a 1. So that's all lining up beautifully. So let's go ahead and figure up our padding. So our padding is equal to 1, because that's our depth, times the 2 hyphens. So we get 1 set of them. So hyphen, hyphen. Oh, hang on, that was a little too close. Looked like one line. There we go. Hyphen, hyphen. So then the next line. So now we just finished this line. Now we're here. Let's print out the padding plus this. So the padding is hyphen, hyphen, and this is C. Ooh, we're still lining up beautifully with the console from the left-hand side. Okay, so next thing we do is we fall down into a for each for his children. So the first child we're going to point to is going to be E. So once again, here we go, setting up a stack frame. And on the stack frame, we just called on E's ShowTree method. E, of course, containing an empty list of children. And what is the depth set to? So once again, we just pulled out E's ShowTree, and we sent C's depth, which was 1, plus 1. So 1 plus 1 gives us 2. Let's take a look at where E is at up on our hierarchy. Hey, what do you know? Look at that. E is at level 2. So let's go ahead and figure out E's padding. E's padding is equal to 2 sets of the double hyphens. So there's 1 set. There's the second set. So we got 4 of them. So we just figured up our padding. Next line, let's go ahead and write out the padding plus this. So 1, 2, 3, 4, and this is E, because of the override that we have in place. Okay, so in other words, print out its name. Very nice. And now what are we going to do? Very next thing is let's loop through all of his children. Well, he doesn't have any children. That means we're done with the method for E. So E is removed. This stack frame is removed. And we return back up to the caller. So here we are back on C, and we just finished the child.showTree for the first child in the children list of C, meaning E. Boy, that sounds confusing. Okay, so what do? That means we go back up and we pull the next child out and store it in child. So the next child is what? Next child is F. So here we are now pointing at F. All right, so pointing at F, once again, we recreate a new stack frame because we're calling upon F's ShowTree. So here we are with F. F, of course, has its own list of children and its depth. Well, its list is empty. And what is its depth? Well, its depth is equal to the caller, which was C, is equal to his depth plus 1. Well, his depth is, once again, a value of 1. So 1 plus 1 gives us 2. And again, verifying the level of F, it's at 2. Right there. All right, so that works. So here we go. Once again, padding is equal to dash dash times depth. So padding equals dash dash, so there's our first set, dash dash, there's our second set. So hyphen hyphen times 2. All right, so now that we have that, our next line is going to write out padding plus this. So padding is going to be 1, 2, 3, 4, because that's what we've got stored. And then this, which is F. Fantastic. Look at that. Our right-hand side console, the one where we just did the trace through,
is identical to the left-hand side where I said this is the result I would like for us to see. Ooh, that's fantastic. But let's make sure nothing else breaks. All right, so we simply printed that out, which means we now fall down to the for each child and children. Well, F has no children. That means we are now at the end of F's ShowTree method. So that means F is now removed. The stack frame, that is. And we return to its caller, which was back up at C. So back up on C, right here is where we just left off, calling upon F's ShowTree. So now we come back up and we go to grab the next child out. Well, there are no more children in C. So here we are over here in C. We've already addressed both children, E and F. So that means we're done, which means we hit the end of its ShowTree method, which means this is removed. And we return back to its caller, which is all the way back up here. That means we return to A's loop, where we were just at, the ShowTree for child C and children. So now what are we going to do? Look for the next child in the list. Well, there are no more children. We've done B and we've done C. There's no more children left to address. So that means we're done. We can simply exit out and we can remove this as well. And there you go. Our representation that we just traced through on the console right here matches what we set out as our goal. Logan, anything you want to add to that?
Nothing I can think of.
Yeah, that was pretty long. You still with me?
Yep.
Okay, excellent. So now what we need to do is code this in and test it so that we can start seeing that our hierarchies exist. As a matter of fact, Logan, what would be awesome would be to create this very hierarchy and make sure that the representation we get on the console, the real console, matches the virtual console that I'm using here. So go ahead and jump over into Visual Studio. And let's start off first with ShowTree.
All right. So let's scroll down a little and find our ShowTree. The first one we want to code in is the one we've been addressing on the whiteboard, the private version of ShowTree that takes in a depth.
Okay.
Now, the first thing that we need to address inside of ShowTree is to set up our padding. Padding is going to be a string variable called padding, and I'm going to initialize it to an empty string. We'll then immediately turn around and pad out the padding variable with dashes depending on our current depth.
Okay.
We can do this by saying that padding is equal to padding dot pad left, and we'll feed pad left our current depth for its total width, and we'll also feed it the character we would like to use for actual padding, and that would be the dash character. Okay. Now, one small thing I need to change here is we were talking about using multiple of these characters. The reason we're doing depth times 2, as in the previous example, is because pad left takes in a char, one single char, so we can't use a string here like dash dash.
Right.
So instead what we'll do is we'll feed it a single dash, but then we'll multiply our depth by 2, giving us 2 dashes per level.
All right, that works out perfect.
All right.
So we still get the exact same thing.
Right. It's almost like what you had drawn on the board, except instead of depth times the dash character, it's depth times 2 for the dash character.
Yeah, I know.
Very similar. But
I know. Yeah, like I said, it was pseudo-coding.
Exactly.
Okay, so next time let's go ahead and write this out just like I showed over on the whiteboard.
Okay. So we'll write this out to the console with console write line. And we're going to write out the padding plus this. And why can we write this and get the correct name? Well, if you remember back in Node, we overrode toString. So that toString shows the name. So that makes our write line more simplistic, where we have padding plus this.
All right. So now, according to the whiteboard, all we needed to do was loop through all of this instance children list and call upon each of their ShowTree.
Okay. So we can begin a for each loop. And that for each loop can go through all transform node called node.
Let's call it child, just so it looks almost dead on with the whiteboard.
All right. So for each transform node child in children, and there's our children list for this current node. So for each child in children, we'll call upon that child's show tree. Now the depth we'll feed to show tree is our current depth plus 1.
Okay, beautiful. That is almost dead on what I set up over on the whiteboard and we traced through. All right, very cool.
Now, of course, in order to actually call upon this from outside of transform node, we would need to have some public method. And as we can see here, ShowTree is private.
Right.
Now, the reason for this is that in order for ShowTree to work properly, it has to begin at 0. When you begin this recursion process, you always want to begin at depth 0 so that you begin on the left side of the screen without additional padding.
That's right.
And if we were to make this version of ShowTree public, then it would be up to whoever was using it to use it improperly and space things out unnecessarily.
That's right.
So that's why above it we have, well, actually, yeah.
Yeah, let's go ahead and create one real quick.
Yeah. So what we would like to do, if someone outside of transform node were to need to show a tree for a specific node, let's add in a public void show tree, and let's take in no parameters. Since we know that anything other than 0 is invalid, let's not allow anything to be passed at all. And all ShowTree does is call upon ShowTree with a depth of 0. So that way no one can affect what's actually taking place. However, they do have access to ShowTree functionality for any given node.
And it'll be drawn correctly because we know for sure ShowTree will always receive a 0. Now you might be thinking to yourself, well, why don't you just initialize the depth inside of ShowTree to 0? It doesn't work that way because of the recursive nature of how this method works. We have to start out by passing it in because each time, even though it's getting incremented, it always gets passed in. So the outside caller that initiates this is responsible for sending in that 0. And by not setting up this particular public method, and if we were to set this from private to public, we're setting ourselves up for a scenario later on where we could end up accidentally passing something other than 0 in, which would result in a broken render of our hierarchy. So by putting in this public void show tree, it kind of serves as a level of protection, if you will, for making sure that the true show tree method functions properly. Okay? So very cool.
Well, with that now, we could jump back to the main program class and begin setting up that tree hierarchy that you had drawn on the board.
Oh, fantastic.
Before I do that, though, let me build and make sure that everything is working. And it has indeed succeeded.
Okay.
All right, so going over to program. Let's set ourselves up an example hierarchy. So let's make a bunch of transform node variables. Let's see. Let's begin with transform node. I'm going to name these node A, B, C, and so on to match the ones that you had on the board.
All right, sounds great.
So we begin with node A. We want to say that node A is equal to a new transform node, and I'm going to feed in the name A, so that once we finally get to the console, we can see it drawn out as we were intending to.
Okay.
So that would work for node A. Now we know we have nodes all the way up until F, so I'll go ahead and create all of those. So this will be B, C, D, E, and F.
Okay.
And we'll name our references and our actual nodes appropriately. So B, C, D, E, and F, and have their actual names be the proper names. D, E, and F.
All right, fantastic. So now we can start some parenting. Like, let's say node B is going to be parented to node A.
Alright, so we'll take node B, call upon its setParent functionality so that we can parent it to node A. Alright?
Okay, and that's probably good enough right there. Let's go ahead and call on node A's show tree.
Okay, so node A dot show tree. Nothing to take in because the public version of that has no parameters.
And let's make sure we have a console.readline just to halt things. And we're not going to see all of our nodes here, but we should see A, and then under A, hyphen, hyphen, and B.
All right, well, let's run and take a look at the output.
Wow, check it out.
And B parented to A.
It's dead on with what we just did over on the whiteboard. All right, so far anyways. But what if I want ShowTree to actually show me, you know, C, D, E, F, all at the root level because they're all root nodes. So at the moment, this show tree that we have works great for starting at a node and showing all of its descendants. But I want to see everything.
Right, if you want to kind of a scene-wide show all.
How can we fix that?
Well, if we go back to one of the methods that we had skeletoned in earlier, we have a static show all for transform node.
Okay.
So what we could do is, since we know that ShowTree works great at if you send it root nodes, you can send it a root node like A, and then it'll show that entire branch for all of A.
So
Very
if
good.
we were able to, say, walk through all root nodes, and with each root node call on their show tree, we'd have everything.
Exactly, we'd have everything in the scene. So let's do that. Inside of show all, let's loop through all of the root nodes. So we'll set up a simple for each, where we say for each transform node in root nodes.
Sounds good.
So for each one of those, we want to call upon node.showTree, and I'll pass it 0.
Yeah, in this particular case, we know this is a one-time coding deal. We know there's no reason to call just show tree, the overload that takes in no parameters, for the simple fact that we know we require 0. This is internal to the transform node class itself, so why put the middleman in there? We can take him out and just directly call show tree and pass it 0, because this will stay at 0 forever.
Exactly. Why throw this show tree on as a stack frame when we can just jump down to what we know we need to be doing down here with depth?
Precisely. All right, beautiful. Now let's see what we get.
All right, let's jump back to program and temporarily comment out this node a.showTree and put in transform node
Because it was a static method.
show all.
Nice.
And this should result in
Ooh.
all of our nodes.
Fantastic. All right, so let's go ahead and close that. Let's take a real quick look over here at the whiteboard once again. Whoa, it's kind of scary. All right, so we've got B in place. So C is also a child of A. So let's go ahead and jump back over here and parent C into A.
Okay. Let's take node C and set its parent to node A.
Node A.
All right.
All right, so let's see, back over here. We have D is a child of B. So let's go ahead and parent D into B.
All right. I'm going to get a little lazy and start copying things. So we need to put in a line so that node D is parented to node B.
All right, let's take a look back over on the whiteboard. So now all that's left is E and F. So let's make E and F both, let's parent both of them to node C.
Okay. And paste in 2 more parenting lines. So we take node E and node F and parent them to node C.
All right, let's run it. Wow, A, B, D, C, E, F. So bump, 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 bump. Let's take a look. So we'll leave that up. Take a look at this. Bring up this. So 2 goes for B, 2 goes for B, 4 goes for D, 1, 2, 3, 4 goes for D, 2 for C, 2 for C, and we got 4 for E and F, 4 for E and F. Oh man, our rendering engine worked dead on. How beautiful is that? But now we also have the ability to render out from a particular node its hierarchy, meaning we could start at C and render out C and then show its 2 children as E and F. And now the nice thing is, since we tell C to show the tree starting at C, C should be slammed all the way back up against the left-hand side of the console, and E and F should only be basically pushed in by 2 hyphens each, because when we call upon C, we know that when we tell C to show its tree, that it's being protected in such a way that 0 is being passed in as the depth as we start to really render this out. Because we don't want it all pushed in. It would look kind of funny because we'd be like, okay, who's he a child of? We just want to see that branch as if it was the root. So let's go ahead and close this out and jump back over here. And go ahead and demonstrate that, Logan. Show us how we can show just branch C's hierarchy.
Sure. I could temporarily comment out the show all, bring the show tree back in, and change this to node C. So we're calling upon node C's show tree. Show only the branch from C. If we run, we see C shown as the root, with E and F both padded in by 1 level, or 2 dashes.
All right, so now let's have a little bit of fun. Go ahead and close that dialog out. Now, at the very end of all of the set parents, let's go ahead and set the parent of node C to node D. Yeah,
okay.
That sounds good.
Let's take node C dot set parent to node D.
And let's go ahead and just show all.
All right, let's bring the show all back in and let's run.
And check it out. It makes complete sense. B is a child of A. D was a child of B, as we saw. Now C becomes a child of D with C's two children, E and F, tagging along. So you can notice all the indentation is working beautifully. That's fantastic. Good stuff. We are also now able to verify that set parent worked correctly, where C was a child of A, but has now been yanked out of being a child of A and has now become a child of D.
We've got another idea of something to check. Let's stress the set parent functionality a little bit more by showing the result of the hierarchy before we run the set parent. So what I'll do is I'll grab a copy of this show all. So we set up our parenting as it was on the whiteboard and show it. Then we could do something like a console write line to indicate what we're about to do. So write out saying testing a reparent. So testing, reparenting.
Okay.
And then we reparent, and then we can reshow. Like so.
I actually got two sets of show-alls.
Whoops. And yeah, you can now see them. So let me comment out the final
Sure.
one, just so we don't reduplicate this one.
Okay. All right. So we got before, which is right. So B and C are children of A. After. Only B is a child of A. C is a child of D, like we've requested. Now let's do one more testing reparent and take C and set its parent to null.
Okay.
To show setting C to the root.
So let's jump down and copy these two lines. So we'll do another test of reparenting where we take C and do a set parent null. And then do a final show all so we can see what the result was.
Okay. Oh, sweet. So our first one, our second one, the third one. B is still a child of A, D is still a child of B, C is at the root level along with A, and it still has two children, E and F. So from the root, we have two separate hierarchies, A's hierarchy and C's hierarchy. That's beautiful stuff. Logan, it looks like our set parent is working great. It also looks like our simple rendering engine is working great as well. Is there anything else that you'd like to add into this?
Nothing I can think of. Everything has amazingly worked exactly as expected.
Excellent.
That's very cool.
So the bottom line is this. If you have a hard time understanding what's happening, watch this a couple of times. It is very, very important to be able to clearly see what is happening with our stack. This is very important. You have to know what instance you're within at the moment when you're talking to a show tree. Okay? And with that, that is going to wrap up this video. Thanks a lot, guys.